Calculus review, algebra review, section 4, logarithms and exponents. I put these two subjects together in this section, despite the fact that they're generally different sections in textbooks or in even our derivatives and integrals chapter where we deal with logarithms. They each kind of get their own second section for that. I put them together here because they are basically the same thing, just like multiplication and division are basically the same thing, just like addition and subtraction are basically the same thing. Logarithms and exponents just undo each other, and so they're very intimately related. One thing to keep in mind when you're doing these problems is an exponent. Most people understand that. We do like 5 to the third power, and what we get is some big number that is 5 times 5 times 5, which is 125. 5 times 5 times 5, 125. And most people are cool with this notation and know how to use this. It's the logarithms that tend to trip a lot of people up. And using this exact same problem, we can show the undoing way of doing this with logarithms. So the way we do that is, if we think about the terminology in our exponential problem, this is like the answer, this is the power, and this is the base. So base, power, and the answer. They're called the same things in logarithmic form. We always have log, base, whatever our base is. So log base 5 in the case that I have here of our answer, 125, will be whatever power you raise 5 to get 125, which is 3, because we know it's that. So the power is always the output. So outputs of log functions, or logarithmic functions, are exponents. Like they're up here. So this is the power you raise that to get that. All right, let's move down and look at some rules. So first important rule is that, let's start with the exponential rules here. When you multiply exponential expressions like this with the same base, so they both have a base of 3, 3 to the 7th times 3 to the 9th, you just end up adding their exponents. We can do this with things that have x to the x is the base, that's totally fine. X to the 5th times x to the 7th is just x to the 12th. Additionally, we can do things with variables also in the top there. So if we do x to the x times x to the x, well, it turns out x plus x is 2x, and so this would just be x to the 2x. So you just add the exponents when you multiply exponential expressions with the same base. All right, now if you divide them, you just subtract. So if we had x to the x divided by x to the x, maybe it makes sense that we'd get x to the 0 out, because we'd subtract their exponents, which happens to be 1. And since it's the same thing divided by the same thing, it makes sense that we get 1. If we did x to the 7th divided by x to the 5th, our same numbers as over here, we'd get 7 minus 5 is 2, x squared. And so that's it for division. And last thing is, when you raise an exponential expression to a power, you multiply their exponents. So a situation where this comes up a bunch in our class is when you have something like x cubed plus 8. How do I want to do this? Yeah, let's just do it to the fourth power here. If I ask you how big is the order of this function, so like the biggest power term in the function, we don't need to know how to expand the whole thing. And if you want to know how to expand the thing, you can look in section Algebra Review section 3, I believe. And it has long and synthetic division and, no, it's an earlier one, 2, which is expanding binomial expressions, which is this one. But anyways, our biggest power function here will be this guy times itself 4 times. So that'll be x to the third times x to the third times x to the third times x to the third, which we know from adding is x to the 12th. And should be a pretty compelling proof that when we raise an exponential expression to a power, we end up just multiplying their powers. 4 times 3 is 12, 3 plus 3 plus 3 plus 3 is 12. And we can do this with like simpler examples like the one I have there. We can just do x to the 7th times, or to the 16th power. And this is x to the 7th multiplied by itself 16 times. So I could write out all those x to the 7ths, or I could just multiply their powers. And so 16 times 7 is 112. And that's it. All right, next stuff, logarithm rules. These are what tend to be harder for folks here. So the first thing is when you have an expression that is raised to a power inside a logarithm, it does not matter what the base of the logarithm is. You can pull that power out in front. So I want to show you an example and then a counterexample of this. So instead of using log base 10, I'm just going to use natural log because we use natural log way more in calculus. So natural log of, let's do x to the 5th. I can totally rewrite this as pulling the power out in front, 5 natural log of x. Sorry about that. All right, next, I want to show a counterexample. So natural log of x to the 5th plus 1 inside here. This I can't do anything with right now. There's the whole inside is not raised to a power, whereas here the whole inside was raised to a power. So I can't apply this rule here. I can't pull that 5 out, whereas I could here. So you got to be careful that the whole inside's raised to a power before you pull that power out in front. Another thing to think about when you're doing these kind of problems is this makes a ton of sense if you think about this in terms of powers. Remember, the output of a natural log, whatever this is equal to, is supposed to be the power that I raised the base to in order to get the inside. And since this is already a power on the inside, I can just kind of pull this out, figure out whatever power I raised that bottom to, and then just multiply it by the power that I pulled out. And so if you think about the output of natural logs in terms of powers, this rule makes a lot of sense. All right, let's look at our next rule, which is that log base e of x is natural log of x. So e is 2.71828 and then more decimals and stuff. Now it's a really special number because it's the solution to the interest rate equation. Like if you take this as x goes to infinity, which is implying that this is your interest rate, this is how many months go by if you go by, or how often you apply interest. If you apply interest very often, so continuously you can apply interest, you're going to get the maximum interest rate. And so this equation will give you the maximum interest rate that you can, or amount of interest you can receive at like a 5% interest rate. So that's what E is. The reason E is really important in calculus is that this function, y equals e to the x, it turns out this thing, because it's the infinitely compounding interest rate thing, it's the special thing that slope is exactly equal to the height of the function at every point. And that's like super awesome and really interesting and cool. But that's why E is important. It basically makes calculus questions way easier. We tend to think about almost everything in terms of E. And so knowing that natural log is just log base E of x, it's just the base. 2.71828. Not a whole lot different than log 3, but a ton more special because of all the properties that come from it. So don't be afraid by E. All right, next thing. When we multiply things together inside, we can just split it into two logarithms that are added together on the outside. So let's think back to an example like log base, let's not do b, let's do like 8 of x squared. I did this one because we have another way of doing this. We can just pull the 2 out in front. So let's do that the first time. 2 times log base 8 of x. So we know this is the answer using the first thing up here. So let's do this now the multiplication way. So this is log base 8 of x times x. So I can just write this as log base 8 of x plus log base 8 of x. And hopefully you notice that these are exactly the same, giving an indication that this might be a pretty legit method. Now, way more often use this in much more complicated cases, like if you want to do the log of, let's do like x squared minus 4 times x minus 3, something like this. And you want to split this up, all you have to do is just do log of x squared minus 4 plus log of x minus 3. So not too shabby. That's it for that rule. So that again is our multiplying on the inside, adding on the outside. All right, now when we divide on the inside, we just subtract on the outside. So let's do a combo problem. Let's do log base 3. Again, the base doesn't matter as long as it's consistent throughout the problem. Let's do x minus 2 times x plus 1 over x squared minus 1. And I can rewrite this all in terms of multiple logarithms, which actually is something we're going to do a lot because it's super useful in integrals and derivatives of logarithms. It's way easier to just deal with a bunch of little expressions than deal with one big mess of a problem. So I can rewrite this as log base 3 of x minus 2 plus log base 3 of x plus 1 minus log base 3 of x squared minus 1, because I subtract the one that's on the bottom. Whoops, sorry, I went off the page. So I just add the ones on top and subtract the one on the bottom. That's it for that rule. And our last one, and often a very, very important one, it's actually how we do any of our derivatives and integrals for things with different bases, is we just change the base of things. Is that we can change log base 7 of x to something we want. Generally, we want natural log of x, by just saying, hey, this thing is just natural log of x divided by the natural log of 7. This used to be how you had to do logs of any sort of different base on calculators, because they didn't have a like the TI Inspires or TI 84s have, where you can plug in the base of a log. So back when I did logarithms, I always had to do this, and it was honestly kind of a nice thing because this is a super important equation that allows you to convert things. This is just the number. It's actually like really close to 2-ish, because 2.71828 squared is really close to this. So really all you're doing to convert from this base to this base is just dividing by that thing, that factor. And that's it. Okay. That's logarithm rules.